Bismillahirrahmanirrahim. Can you hear me? Anyone please respond? Yes. Ansu Khan. Vaniza Arbab. Anyone please? Muhammad Rahman.
Yes, sir.
Okay, if there will be any distortion in the voice or stillness in the screen, please let me know. Bismillah Rahman Rahim. Today we will discuss about algorithms and data structures. Computational complexity. What is the complexity in computational space, computational time, and what hardships usually we have to face about that? So, in an algorithm, you know that algorithms are the series of steps to solve a specific problem. The most important point here is the algorithm should be shorter and the algorithms should be fast, so you can get your output in minimum time span. So what will be the desired properties of a good algorithm? As we already discussed that any algorithm should have two conditions that will make that software, that algorithm, a good algorithm. Complete compute correct output, and the algorithm should be effective and fast. So these two properties should be present in a good algorithm. So the algorithm should have the capacity, or you can say capability, to compute the results in correct direction. Output should be good and effective, and the algorithm should be fast and take very minimum time. Correctness of the algorithm and complexity of the algorithm should be considered in this point. Complexity of algorithm measures how fast is the algorithm and what amount of memory it uses, time and memory, basic resources in computations. For a good algorithm, first you have to design the series of steps to solve a problem, and the output should be correct, and the algorithm should be short, and algorithm should be fast. The search, what is the search problem? So problem of searching a key in an array. We already discussed about the array. Suppose we have an array of 10 integers or characters maybe. So we want to find a specific number or specific information from the array. Suppose on the fifth slot, what information is present, or maybe you have x is equal to 9 and you want to find this from the array. So this you have to search this specific number. So problem of searching in an array, what does the amount of work of this algorithm depends on? The first question is that if the array is of 1 lakh digits or integers or characters, then the search problem, it is a you need much time to search. And if the array is small, then you need small time to search. So however, you need some time. So in this case here in the third slot, we have find array length and key. Three specifications we have. First of all, we have the array as an input, or any integer or character depends on the generation of that array, and then you know about the length of the array. Suppose the length of the array is of 1 lakh or maybe 10. In 10 you just find it very easily. However, if there is 100,000 or 10,100,000 integers in that array, then it will take much time to solve. So integers you have to find is that specific key. So here we have an example. Here we just run a while loop in a search problem, like output integer should be 0, or I should be less than and equal to 0, or here I we have I should be 0, less than and equal to 0, and greater than length. So being the index in array under which the key is sorted, or the value of -1 if there is then no specified key in the first position of the array should be present. So here we have a code like we want to find an array from an array a length a key I is equal to 0, then we will run a while loop I is smaller than length. If array is I, then the key should be present, and if not, then return and plus 1 plus 1 plus 1 plus 1. However, if the return is a minus 1, then we will have nothing. What does the amount of work for of this algorithm depends on? So the speed of the algorithm to measure how fast the algorithm is or how slow the algorithm is, there are two specific issues to be considered by while designing the specific algorithm: the independency of the programming language, that which program language you are going to use, you are independent in that. However, you have to design the algorithm in the shortest way and the effective way, no matter which language you are going to use. And the second point is maximum independency on particular input data, that you want, you have to take data from the user in many fields, and you have to give independency to the user while giving the input data. It should be an internal property of the algorithm. So count the basic operations of the algorithm. What is the basic operation of the algorithm? That will cover the most appropriate position or represents the most of the data, should be the basic operation. Suppose if we have suppose we have the marks of our students in the class, and we will represent the marks like everyone has more than 80% or 70% marks, so it will represent maximum of the operating basic operators. So what will be the dominating operations specification? It is not necessary to count all the operations. It is enough to count the representative ones. So you don't need to count all of them. You just have to take the representative one that will represent the major portions of the operators. Before doing a complexity analysis, two step must be done: determine the dominating operation set, as we already discussed what it will be the dominating operating sets or basic operating sets that will represent the maximum portion of the specific data. So first we have to determine that which those operating systems are, and then we have to observe that which input or what type of input has the influence to the number of that dominating operators or data size. So dominating operators are those which covers the amount of work which is proportional to the whole amount of work of the algorithm. As we already discussed that the dominating operations are specifically those operating sets that represents the maximum number or the huge amount of work from a specific data set. So first we have to determine those, and then we have to observe the number of dominating operators we have in our data set. Here we have again the same example, that the same code we have here to find a specific key. If and we are running a while loop here. So question is here, what will be the dominating operators from this code? So assignment I is equal to 0, is it a dominant code? No, because 0 is just denoting one, only one. So it's not representing the whole data or the maximum number of the data. However, in comparison with I is smaller than a length, question mark means yes, because whole length, it is denoting the whole length, the maximum number of the data from the array. Similarly with the array I, whole array, if we are going to compare our key with the whole array, now again we are representing the whole amount of maximum amount of data. Similarly, if we are just going to check both of these, then again we are just having a large amount of data. However, if we are just going to check my I in return, that is only one, as we have I is equal to 0 and return 1. These only two represents one data, not the whole data here. So increment also just representing plus 1 plus 1 plus 1 again and again and again and again. So it's also representing the large amount of data. So in this case we have I is equal to 0 and return minus 1 will not be the dominating operating systems, because this two only presenting only two digits, not the major portion of the data. However, when we just compare I with the length or array I with the key or return I plus plus, so it represents the large amount of data. So determining the data size, again same example we have, and length of the array is the data size, how many integers you have in the length. That will be the data size, and from that data size we have to determine the dominating operating system. So time complexity of the algorithm, it's the most important you can say step or considerable point for designing an algorithm. That time complexity of an algorithm, the number of dominating operations executed by the algorithm as a function of data size. Time complexity measures the amount of work done by the algorithm during solving the problem in the way which is independent on the implementation and particular input data. The lower time complexity, the faster algorithm. As we already discussed, that the problem will be solved in the most least time, will represents the best software or best algorithm. Suppose you are just want to check a specific number from an array, and the algorithm is taking so much time, then it's not good for you or not good for the audience. So the complexity of time is very important, that the algorithm has to give the input in minimum time, the shortest time it has, and the number of dominating operators in that specific algorithm has to execute by the algorithm. So algorithm can check all the representative data. It doesn't mean that if you are going to short the time and you are just going to skip a large amount of data information. You have to check all the data from you have to check all the dominating operators from the data, so you can represent all the data. So here we have time complexity of algorithm, same we have the same code we studied in earlier. So we assume that dominating operation comparison is array is equal to key, and data size is the total array. As we know, the number of dominating operations executed by the algorithm ranges from 1 to n key. Here we have suppose we, if you just remember or recall the array concept of array, that we have an array and we have a number 1 to 10, and we have to check from first number to last number for to find the key. If we are not getting the key, if suppose we get the key at the fifth slot or sixth slot, we will give the answer. So there is no single function which could express the dependency of the number of executing dominating operators on the size, data size of this algorithm. So here we have one more important concept, that is P and NP informally. So first we just try to get what is algorithm, series of steps, what is the desired properties of an algorithm. The most important property is that the algorithm should be faster and efficient, and the output should be good. Then we are independent to select a specific language, and we should have to give independency to the user to give a large number of options for inputting of input data. Then we have a concept of time complexity. We have to find out the basic operating sets, or you can say dominating operating sets, that represents that has the capacity or ability to represents large amount of data, and then you have to execute all the basic operating systems, so you sets, so you can check all the data for the results. So here we have the concept of P and NP informally. P and NP are two classes of problems that can be solved by computers. P problems can be solved quickly, like it's very easy problems, or 2 plus 2 4, 100 plus 100 200, these types of problems, or very small problems that can solve very quickly, and quickly means in seconds or maybe in hours. So that all are the problems lie in the class of P. However, NP problems can be solved slowly. Slowly can mean 100 hours or 1000 hours or sometimes years or months. So there are two types of problems we have classified here. First, the P problems that can solve very early, and however, in NP problems we should need 100 hours, 1,000 hour, years or months to solve that specific problem. So an equivalent equation we have here, like is there a clever way to turn a slow algorithm into a fast one? Yes, we can turn a slow algorithm into fast one, but we should have to be very careful about the efficacy and effectiveness of that specific algorithm. If p is equal to np, the answer is yes. If the p problems that we can solve in minutes is equal to np, then we can change the algorithm from slow to fast. However, if p is not equal to np, like we cannot solve the big problems in small time. Like here, if p is equal to np, mean that the np has big problems, but we can solve in less time is equal to p. However, if the big problems we cannot solve in with the smaller time like p, then the answer is no. If we will make it fast, then we will skip so much data, or the result will be not much good or effective. So why do we care about that? People like things to work fast because people don't have much time to wait for the algorithm to run. So people need the result quickly, so they want to save their time. So encrypting information. So what is encrypting information? That is some secret information, or the information you don't want to lose or you don't want to give to others. So if there is an easy way to turn a slow algorithm into fast one, there is an easy way to crack the encrypted information. When you just make a slow algorithm to a fast algorithm, then you will give a chance to the crackers so they can easily crack your encrypted information. And this is if they will get your encrypted information, that may be the information of your staff, your civil services, your information, your university data, or any type of data they can take from you and they can sell it out. So you should be very careful about that, that if you want to make the software algorithm fast for the demand of people, you have to keep in view that they cannot crack the encrypted information. So most people think that p is not equal to np. No, p is can be equal to np. Like if suppose np are not much always big problems, it can solve with the help of p also. So in general computing, what we have in actual, the basic concept, we just give an input, then there will be a program that will run or execute, and then we have an output. This is the basic concept of computing. Suppose you give 2 plus 2, here we solve it as a 4, and then output is 4. So this is the general computing, the concept of a general computing. However, when you have some crash, when you have a lot of time to take the output, then we have some problem here in program input. Then we have program, however program is not running well, or the output or input is not matching, or input is not appropriate, or output is not appropriate, or algorithm is slow, or there is some steps missing in the algorithm. Anything happened here at this step, and then we have no output, and sometimes we have crash, or sometimes our computer is running again and again and again and again. So in general computing, when we have some problem, the problem is an actual here at the time of programs. So what happen when things get stuck? Suppose we give input and we give a number x. So here we have a program that L1, if x is smaller than 15, or if x is greater than 15, output should be 1. Otherwise, go to L1 again, to this L1 and check. No, now we don't know how many numbers we have in L1. So what is the output? 1 if x is smaller than 15 or greater than 15, then never stops otherwise. If it will get the result from here program, suppose the first query we will get the result, then output will be there. However, if there will be no 15 or 16 or the specific number, then again and again go to L1 and check. So it will not stop. So it will run again and again. And if you will get your result, then you will have the output. And if you don't get the result, then you will stuck here at this point. A couple of things to note, that there are lots of programs available for a specific problem. So some are faster than others, so we can always artificially slow them down so we can, yeah, get the good results. So what was we were discussing about P and NP, as we already discussed that the P are these are two classification of problems. P are the problems that we can solve in very slow time, or in minutes or in hours. However, NP problems we need hundred of hours, or thousand of hours, or sometime years. So P and NP are the classes of solvable problems. So in short, we can solve these problems. In P we need less time, however in NP we need much time. Solvable means that there's a program that takes an input, runs for a while, but eventually stops and gives the answer. Here we have a computation tree for solvable problems. So how we can solve a problem? Here we have an example that we already discussed, that input x, that is L1 if x is greater than 1, then set x is equal to x minus 2 and go to L1 if x is equal to 0, output 0, if x is equal to 1, output 1. So here we have the program. Like in general computing, we have an input, then we have a program and output. Similarly, here we have a program that we are going to run. So how it will run? Input x is equal to 3. What will run? What we have running here, x is greater than 1, so x is equal to this formula we are applying here, 3. That input 3x3 minus 2 is equal to 1, x is equal to 1, so output is 1. So here we say that if x is equal to 1, here if x is equal to 1, output we have to know, we have to show 1, and if x is equal to 0, then output is equal to 0. So here we have, in two steps we just solve it. We just give the input as x is equal to 3, it solve it here, that if x is greater than 1, then we have to minus 2 from that x statement. Suppose if we have here as a x is equal to 5, suppose instead of 3, then we will solve it like x is equal to 5 minus 2 is equal to 3. Again we our x is greater than 1, again we just add x is equal to 3 minus 2 is equal to 1, then the steps will be increased, and until we will get x is equal to 1 or x is equal to 0, we will not stop the program. So that was the in actual computation tree. So more about the example, what does this program do? Output 0 if input is even, and output 1 if input is odd. From the previous computation tree we can observe that if the output is 0, input should be in even numbers, and if the output is 1, the input should be in odd numbers. So solve the problem, is the input is even or odd. So here we have the same concept about the length of computation tree, that if the time is 3, then it should be about 2, 4 by 3 x, and x by 2 plus 1. Suppose x is here 7, then 8, suppose x is 8, 8 over 4, 8 by 2 is equal to 4 plus 1, then we have 5, and again we just move to the 3 position or 4 position to go to 2 or 3. So what is about solvability versus tractability? A problem is solvable if there is a program that always stops and give answer. So problem can be solvable when you have the answer, and if you did not get any answer, then you can say the problem is not solved yet. So number of steps it takes depends on the input you have. So how many steps we are going to run? Like we just already have a look to the example, that if x is equal to 3, then we just have one computation tree, suppose, and if x will be 5, then we have 2, and if x will be 7, then we have 3 steps for computation. So in short, we are going to solve the problem. How many steps we need, it depends on the input of that specific data. Problem is tractable or in the class P if it is solvable, and we can say time is almost some polynomial. It will take much time. Time is some polynomial, as if you remember the concept of mathematics from your high school, that is polynomial or non-polynomial. In some polynomial we have here. So p problems are usually fast, as it can we can solve it in minimum time span. So that's why the p problems are in very fast, and p problems are slow because it takes much time. These problems are comparatively fast. For example, consider a program that has time x is greater smaller than and equal to x square compared to one with time x is smaller than and equal to 2x. So here you can say that if x is 2, suppose here we have x is 2, so then 2 into 2, 2 exponential power 2 is 4. However, if we have 4, then 4 4 16, and if we have 4 here, then it will be more. On the input 100, the computation times compares as follows. So and the guy is saying that the example is saying that if x is 100, then we have this value. If 100 into 2 is about 10,000, so then 10,000 calculation is much easier in this time. However, if we have 2 into 100, then we have this value, a big number to compute. So it's easy to compute 10,000 as compared to computing this one. It's very small number. It's very small number. Here x is smaller than x square, and time x is smaller than and equal to 2 into x. So here you can say 10,000 is a very small number as compared to this big number. So what about NP? The description involves non-deterministic programmings, is known as, you can say, n problems, that you cannot determine the program what is happening or how you can solve it. NP stands for non-deterministic polynomial time computable problems, and the examples we have seen so far is deterministic problems that we easily solve with the examples. However, P stands for polynomial time computable. NP is non-deterministic programming, non-deterministic polynomial time computable. However, P is polynomial time computable. An example of non-deterministic programming is here. Non-deterministic programs use a new kind of command that normal programs can't really use, because in P problems, it's small problems, and we can solve it in a very short time, so we don't need to go other ways to solve that. However, in non-deterministic programming, where we need much time, we just usually use different types of commands to solve the problem. So in non-deterministic programming, you just give a guess about the result because you are not sure about the result. However, in deterministic programming or computable programs, you are sure about the result. However, in non-deterministic, you just give your guess, or guess, you know, sometimes it's right or sometimes it's wrong, or you just give accurate guess about that. And sometimes it will give you all the possible responses in non-deterministic programming. Here we have a program again, like last time we have very easy program that x is equal to 1 or smaller than 1 or 15, and otherwise you just go back to the L1 and you can check again. However, here we have input x, guess y in 1249. If you are going to give input x and you have to guess the value of y with the that if y will be 1, what will be the value? 249. Similarly, if x plus y is greater than 10, stop and output 0. If you just going to plus x and y 1249, here we have, but we don't have x, and someone is giving x as 1. So first we have to plus 1 plus 1, then 1 plus 2, then 1 plus 4, then 1 plus 9, and if it is greater than 10, then we have to give the output 0. Otherwise, if y is even, guess z. So we have another program here. Here we have 149, 1249, and if y is even, and other than that, and guess z is 2 or 3. If x plus z is odd, stop and give the output 1. Otherwise, give the output 0. So this program we have to solve. In actual, we have the value of x depends on the user, that what a value it will give. Then we have to check all the given value with these four numbers, and if these plus of these two addition of x into y is greater than 10, then we have to stop the program and we have to give 0. And if we are not going to stop the program, then we have to check that y should be even, and then we have to guess the z, and we have to plus x and y, then we have to give the x and y. It is odd, then we have to stop, otherwise we have to give the result as 1. So here we have the guess. Suppose input x is equal to 7, like we just have y 1, 2, 4, and 9. First we have plus all of them and we will get the result. Here that y is odd, we gave the result as output 0. So here we have y is even, as we can say here, if y is even, 2 and 4 is even, then we have to again use the value of z, that is 2 and 3, then we plus x plus z is equal to 9 and give the results here. So we have these all guesses about that, about their program that is non-deterministic. So this type of path we have to follow. Like here we have three or four or five or six computational steps, and then we can get the result that what is in actual happening in this non-deterministic programming. So that is the guess in actual. Suppose if we have x here as 1, then similarly we have to check with 1, 2, 4, and 9. These two are even numbers, then we have to add the z here. So non-deterministic programs are usually conventional, and if any computational path ends with a 1, the answer to the problem is 1. And if all computational power ends with 0, the answer of the problem will be 0. Otherwise, we can say the computation does not cover the specific number. Again, we are only interested in problems where this third class never happens, that is solvable problems. This one, otherwise we can, computation does not coverage. In these two we have some results. However, if our computation power is not covering the problem, then we cannot get a result, and when we did not get the result, then it's not a solvable problem. So the class np, if the computation halts on input x, the length of the longest path in n time x. N is the number and time x. A problem in NP, if it is solvable and there is a non-deterministic program that computes it so that n time x is smaller than and equal to some polynomial. So non-deterministic problems here, if we want to make them deterministic, a non-deterministic algorithm can be converted into deterministic algorithm at the time of cost. Like if you want to convert a NP problem into a P problem, then you have to give the time, that time you have to bear a lot of time, or you have to wait for a long to solve that problem. Usually the increase in computation time is exponential. This means for normal computers, deterministic ones and NP problems are slow because it takes much time. So here we have this picture that can elaborate that all solvable problems is in this box, and then we have this circle that is NPs that we cannot solve in smaller time. Then we have P problems that we can solve in smaller time. So in actual we have very small window of P problems that we can solve in smaller problems. So what is the basic concept of SAT here? The problem of satisfiability. So here we have a statement of the proportional logic. Like if you just remember the gates you study in your FSC or in your college life, that is truth gates. And here we have the concept of truth gate. If P is equal to Q, or the truth in this case P and belongs to Q, these types of truth gates, if you just going to remind it, it means that in both P or Q, P is wrong, or maybe Q is wrong, or both is false. The problem is to determine if it is satisfiable. In other words, is there a line in the truth table for this statement that has a T at the end of it? This problem can be solved in polynomial time with non-deterministic program. So satisfiability is you can say specifically a specific, in a specific time you are going to solve a problem, and then you are satisfied from that. We can see this by thinking about the process of constructing a truth table and what a non-deterministic algorithm would be. So usually satisfiability depends on, or is a NP problem, not with the P problem, because in P problems, you are already satisfied because you have the accurate guess. However, in non-deterministic guesses, when you have a different guess and you are going to give much time and algorithm is slow and your problem is lying in non-deterministic or NP problems, then your satisfaction is very important, that how much you are going to rely on that specific guess. The length of each path in the computation tree is a polynomial function of the length of the input statement. So NP completeness, if P is not equal to NP, SAT is the witness of this fact, that is SAT is NP but not P. Similarly, it is among the hardest of the NP problems. Any other NP problem can be coded into it in the following sense. If R is a non-deterministic polynomial time algorithm that solves another NP problem, then for any input X, we can quickly find a formula F, so that F is satisfiable with when R halts on X with output 1, and F is not satisfiable when R halt on X with output 0. NP complete problems, here we have problems with this property that all NP problems can be coded into them are called NP hard. The problems we are here going to face is very hard. If they are also NP, they are also called NP complete. And if P and NP are different, then the NP complete problems are NP but not P. So you have to understand the basic concept, that what is the difference between P and NP, deterministic and non-deterministic, and which problems can be from P to NP and NP to P. If P and NP are different, then the NP complete problems are NP but not P. If you just complete the specific problem of NP, it should be NP complete, but not, you cannot say it a P problem. You can say it NP complete problem. So you guys remember this game here, Minesweeper. If you just remember that this game, you have to make a guess. This is non-deterministic type of game. Like here we have two. It means that from these two boxes, these two boxes, these two boxes around this maybe may have the mine. Sorry. Similarly, here we have one mine. So here we have one. So it means that any box from around this one there is a mine. So we have a mine here. Similarly, with this three and two, this two upside two. So this is the guess in actual. Here we have two. So maybe these two, any two side of this two may has the mine. So you have to click this like this way. So this is the concept of Minesweeper, and this is also a certain problem of NP, like you are going to give the guess that where that mine should be in that box, and how efficiently you have to solve, you have to protect yourself from that mine. Similarly, we have another game in our childhood. Here we have to just align that these blocks that we are coming from upside, and we have, if the line is completed with the same color or equally, then it will be lower down. So we have to complete it. That is also the same example we have, that you get to know all the pieces. There will be only a finite number of variant that order they will appear. So if the boxes will reach the upper limit, then you have the crash. So you have to start with a partially filled box and then you have to solve it. So the following problem are NP complete problem, because you can complete it easily. uh, that the non-deterministic, if you are focused about your game. Maximizing the number of rows cleared, so you have to clear the rows. Maximizing the number of pieces placed before losing. Maximizing the number of matrices. Maximizing the height of highest filled grid square over the course of the sequence. So that we have in actual about all the concept of computational complexity, and how we can lower down that complexity, which are the deterministic and non-deterministic problems, what are N and what are P, and algorithms are the series of steps we are going to use to solve a specific problem. And we have you can say concept of P and NP. The P are the problems that we can solve in a minimum time span, that is non that is deterministic problems and polynomial computable problems. Then we have NP. NP is bit tricky, in which we have to take the guess, and the guess should be accurate, so we can easily get that specific uh, results. If anyone has any question. Thank you so much everyone for joining.